I'm Gizusman. I'm in electrical engineering at Columbia University, and I am the Columbia PI of the COSMOS project and the PI of this project.
I'm Harry Choudhury, and I'm a professor at Rutgers University and also director of WinLab, the wireless center we have at Rutgers. I've been part of the management team for the PAWR COSMOS project that Gil mentioned, and have some personal research interest in dynamic spectrum access.
Hi, I'm Carlos Caicedo. I'm an associate professor at Syracuse University and also vice chair of the IEEE 900.5 work group, which is producing standards on dynamic spectrum access. Overall, one of my research areas is dynamic spectrum access in general.
Hello, I'm Fred Moshari. I'm a professor of electrical engineering here at City College of New York, and I'm the director of the NOAA Center for Earth System Science and Remote Sensing Technologies.
Hi everyone, I'm Tingjin Chen. I'm assistant professor of SII-NRDZ at Duke University. Gil was actually my PhD advisor when I was at Columbia, and then my PhD was mostly working with Gil, Ray, and Yvonne on building the Cosmos testbed in the city.
Yeah, hi, my name is Ivan Seska, and I'm a chief technologist at WinLab and also program director at Cosmos and co-PI of the NRDZ project.
Hi, Kyle Jameson from Princeton University. I'm a professor here in computer science. I'm affiliated with electrical and computer engineering. My research lab here has some relevant work on 5G, next-G telemetry, and that's my part in the current proposal, and nice to meet you all.
So I think everybody was introduced. So that's just the title of the project, spectrum sharing via consumption models and telemetry, prototyping and field testing in an Urban FCC Innovation Zone. So that's the topic, and we'll go through the details. So this is really a quick overview, and then I'll hand it off to other people that will talk about the different components. But the idea is to investigate ways to share electromagnetic spectrum using an automatic spectrum management system. We'll prototype a management system for spectrum sharing within and among disparate services such as communication and scientific use cases, and you'll hear about some of the scientific use cases. And we'll use two facilities in West Harlem. One of them is the COSMOS testbed, supported by NSF and the PAWR program, and the other one is the NOAA-CESSRST Center that Fred will talk about. Both of these are actually within an FCC Innovation Zone. So we'll use systems at these facilities for spectrum sharing experiments, and we believe that New York City, which is a dense urban environment, of course, is a stressful case for spectrum sharing, and techniques that will be validated here will function well in other cities in less dense environments. So this is the high-level overview of the project. We mentioned COSMOS, which is being deployed between 120th Street and 135th Street in Harlem. This is the yellow region, more or less. Around COSMOS, we have the FCC Innovation Zone, which is the red region. And at the top here, within City College, which is part of COSMOS, there is the NOAA-CESSRST Center that includes several devices that are quite relevant for this effort. So that's the area in which we operate. The applications that are relevant for coexistence are satellite receivers, radio meters, 6 to 7 gigahertz, radars, and so on. And in order to support all this coexistence, there are several tasks that different people will talk about, and all of them feed into a zone management system. We'll have a monitoring and measurement effort. Carlos will talk about the SCM spectrum's consumption model. Kyle will talk about scalable spectrum telemetry, and eventually these will feed into spectrum sharing algorithms and risk analysis. So, as I already mentioned, we'll prototype a zone management system. The fundamental information model for the zone management system is spectrum consumption models that are standardized within the IEEE 1900.5.2, and Carlos will talk more about those. And basically, we will use those in order to develop spectrum sharing and interference management algorithms that use the SCMs and also measurement feedback to achieve high spectrum efficiency, low processing and complexity and communication overhead, and scalability. And of course, the zone management system will be evaluated via simulations, but also via world experimentation at Cosmos and NOAA-CESSRST. So this brings me, to the outline of this quick presentation. So I'll hand it off to Ivan, who will talk about Cosmos. Fred will talk about NOAA-CESSRST. Then Carlos will talk about the spectrum consumption model, and Ivan will talk about some of the algorithms. And eventually we'll talk about the planned activities within the zone management system. So Ivan, I'll hand it off to you.
So the main idea behind Cosmos, which is one of the PAWR platforms, as we heard over and over, and I know a number of people on the call are actually familiar with it, but just in case that there are people who are not, it's sort of to focus on basically two of the more important components or dimensions of the modern wireless systems, which are the latency and computing power, right? So the idea is to sort of introduce these low latency, highly programmable components, as well as to sort of bring the edge computing as close as possible, or to enable experimentation with computing. And when I say computing, various forms of computing or heterogeneous computing platforms throughout the testbed deployment. So objective is to sort of say, look at the ultra-high bandwidth, multi-gigabit per second type of wireless systems with very low latency and supported by really powerful edge computing platforms. So the enablers are a number of millimeter wave area antennas. So, of course, focus is on millimeter wave in a highly dense urban environment. A lot of fiber, and when we say fiber, we're talking about dark fiber, which is fully focused and dedicated to experimentation. Of course, a lot of edge cloud base stations, meaning capabilities that are very near, computing capabilities that are very close to the antenna. And then, of course, remote access and programmability. In other words, hopefully not too many people need to be in the environment to perform experiments. Now, of course, if somebody wants to do mobile experimentation, then they would have to be in the environment. So this is actually the view from one of our large nodes, meaning from one of the rooftops where we have deployment, looking at the deployment area. And you can actually see in the far, not far that far, but the NOAA CREST, the NOAA deployment, the other testbed that's part of the NRDZ project. And the railroad that you see, the subway that you see coming out of the underground is actually a Broadway, and the Amsterdam Avenue is on the right-hand side. You can't see it actually. And this is on the 120th Street, and it goes up to where NOAA is, which is on 135th Street. So that's essentially the testbed area. As you can see, it's highly dense urban environment. So if you look at it, if you look at the Manhattan, right, on the first picture on the left, the testbed area is actually that shaded green area, and you can see it actually in the middle picture with all the nodes deployed, right? And so the idea is that we have three types of nodes. The large node, which is sort of a rooftop deployment, the medium node, which is street level or lamppost or side of the building deployment, and then what is something that we call jokingly a near portable node, which is essentially a device or devices that you need maybe two hands to carry around. And all three types of nodes are highly programmable, software-defined radio-based type of devices. Now, as was mentioned, one of the key components of the Cosmos testbed is the declaration of FCC Innovation Zone, which sort of allows us to do, of course, with the prior approval, experiments with quite a number of interesting frequency ranges, and you can actually see them here. Of course, in our case, given that we are focused on millimeter wave, quite an interesting ones are 6 to 7 gigahertz and 28 or around 28 gigahertz. And of course, some others if people are interested. In addition to main testbed deployments, we have a number of sandboxes, what's called the sandboxes, which are sort of there to allow people to develop applications and deployments before actually committing to using the testbed itself. And there are a number of sandboxes, both at Columbia and at Rutgers, that are readily available and used for remote access. Now, as I said, we are finishing the deployment in phase 1, and that is actually deployment of large and medium nodes and CCNY at 135th and 136th Street. And here you can actually see how it looks like. The plan is to actually finish the Amsterdam Avenue corridor before soon. And then the interesting part of that is that it's actually a key component for doing experimentation with the other testbed, which you're going to hear shortly about. And that's where the co-location is actually critical, right? And this shows you the relationship between the two testbeds, the Cosmos overlap with the NOAA testbed.
Thanks, Ivan. So I'll switch over to Fred.
I'm just going to say a few words about our center, which is a consortium of 6 universities with the City College as the lead, and the focus is Earth System Science and Remote Sensing Technologies. So really application of remote sensing in Earth System Science. The center itself is quite old. It's about 21 years old. The most recent cycle, which ended up being a 6-year cycle that was completed, essentially we had 244 students engaged from bachelor's to PhD level, and the areas of research that we focused on are coastal, atmospheric, and really the hydrological cycle, so it's called water prediction and ecosystem services, which focuses on the hydrological cycle. We are continuing a similar structure in the focus on the 3 domains for the next 5 years. So some of the facilities that we will be bringing to this project includes our satellite receiving station. The dome that you see, the radome, has a 2.4 meter XL band antenna in it, and it's particularly focused on receiving polar orbiting satellites, which are orbiting north-south or south-north. In the X-band, much of the U.S. satellites are transmitting in the X-band, so the radome, the antenna inside the radome essentially looks at the horizon to catch one of the satellites and then downloads the data as the satellite moves across the sky and sets on the other horizon. So it sort of chases the satellites in the appropriate directions. And certain NOAA and European satellites are broadcasting in the L-band, so we also receive the L-band broadcast from those satellites. The other system that Gil pointed out to is a microwave radiometer that receives in the K-band and higher. It's a hyperspectral, what they call a hyperspectral thermodynamic profiling radiometer, because it essentially is a passive instrument looking at received radiation in a number of bands and computing from that the profiles, actual profiles, vertical profiles of water vapor, and temperature. And the other opportunity that we look to have over this summer and maybe the following summer is that there are a number of campaigns that are planned for the area, and we anticipate that one or more smaller X-band weather radars, which operate around 9.5 gigahertz range, will be tried out during these multi-agency campaigns that are going to be happening in the greater New York area. So those are some of the facilities and instruments that will be able to be deployed, used for this study. Next.
Thank you, Fred. So now we'll switch over to Carlos that will talk about SCM.
Okay, thanks. Yeah, so this is going to be a quick few words on SCMs. So spectrum consumption models are basically a data model that has come about from collaboration by different entities that are participating in IEEE standardization group. The idea, which frankly originated mostly from MITRE, that then has evolved, it was to define a data model that can be used to specify the boundaries of spectrum used by any device in basically in any scenario of communications. So the rationale for this was, as it says in the slide, a common means to define spectrum use. If everybody agrees to that specification, would then enhance spectrum sharing interactions across many different participants or stakeholders, regulators, commercial users, and so on. So SEMs basically try to capture a minimal amount of information to specify the boundaries of spectrum use. So how radiation comes out of an antenna, how it's being captured by an antenna, the power, the antenna pattern, and other elements, which I'll explain later. But the idea was to make this as minimal as possible, but also usable. So the idea is to try to position SEM and build it it was built in such a way that it tries to achieve these goals and can be then heavily used in any type of spectrum management scenario. So with those goals in mind, which again, just to summarize, was to define a data model that provides a way to capture the relevant parameters related to spectrum use, but also make them, let's say, put them in a structured way that makes them usable in such a way that you can compute compatibility between any two systems that are using SEMs to express their spectrum uses. And by compatibility, we mean being able to use information in the SEMs and just that information without reliance on any external data. So use the information in the SEMs to determine if two or more devices will interfere with each other or not. That's what we call compatibility, being non-interferent. So these goals were then captured in a formal specification at the IEEE 1900.5.2 standard. So SEMs rely on, or basically the standard specifies a data model that relies on 11 pieces of information. We call those pieces of information the constructs. So you can see the list here. So these are items that, again, allow you to capture how radiation is being emitted, antenna characteristics, location characteristics, schedule characteristics, and so forth. Not all 11 elements are required for every single spectrum consumption model. Some are optional. Some are just required for transmitters. Others are required for receivers. So it's not that you have to check all these boxes, but there's plenty to choose from. There's a lot of flexibility to specify any type of spectrum use in any environment. So the idea is that those constructs can be used to build transmitter models and receiver models. So those are just two types of SEMs. Those two basic types of SEMs, transmitter models, receiver models, then can be aggregated into system models. Those can also be aggregated into set models, and then this aggregation facilitates compatibility computations, so facilitates using spectrum consumption models, the higher levels of these constructs, to specify authorizations or constraints to spectrum use in a given area by shaping the information in the SEM. How models are built, it's really an art. There's no specific way to do it. The standard doesn't specify how to build the model, so actually modeling from scratch, as it says here, requires that there's an engineer that understands the system that's going to be modeled, has the information about the antenna characteristics, the power characteristics, the location characteristics, and then can use that information and put it in the format that's required for the SEM. The idea is that you can then build tools on top of SEMs to facilitate spectrum management interactions. In our case, build the some management system based on SEMs. So to make a long story short, the information in the SEMs basically allows you to build a very detailed power budget computation to determine well, if you have a transmitter in this location and with these transmission characteristics, antenna characteristics, environment characteristics, this is the expected power of that emission at this location, and then you have a receiver somewhere down the line near that location. You can then determine okay, if this is expected power that's going to come out of this transmitter, and I'm this receiver, and this is how my antenna is structured, my receiving filter is structured, and so forth. Will I be capturing enough interference from that transmitter to consider it harmful interference, yes or no? So that's kind of where the compatibility computation goes, and it's just based on the information captured in the STMs. So a little caveat is that to actually do the computation, first you determine, okay, are these two devices going to overlap in time and in spectrum? If yes, then you start determining, okay, what's the kind of the worst case scenario for interference for these two systems, and then use the information in the STMs to determine if there's going to be compatibility or not. And STMs, we can also specify not just static locations for transmitter and receivers. We can specify trajectories, orbits, and things like that. So, but a challenge is kind of detecting these worst case scenarios, worst case locations, worst case timings, and that's part of some of the research that needs to be done. But the information
just because of the time, I'll flip a few slides forward.
Yes.
Ivan can give a couple of examples of how this is used, and then I think we need some time to say a few words about what we plan to do.
Sure. So just to sort of, this is more like historical than anything else. So in order to sort of start putting all these concepts to sort of practical use, we sort of had to actually put it together, and in addition to dealing with STM, sort of put the whole system together to be able to measure what's happening with the spectrum, as well as to sort of try to put together a way to communicate between these various components of the system. And so first part of it was try to capture what's happening in the very large pieces of spectrum, and to that end, we sort of developed this FPGA-based spectrum sensing. This is just sort of illustrating the ability to do sensing, and this was done quite a few years back, sensing at 160 megahertz, and this was actually one of the key components for the physical layer that we used as part of our implementation for the SE2 as part of the DARPA Spectrum Challenge, right? The second Spectrum Challenge. And again, this was also sort of, the idea came in after using the so-called SIL, which was collaboratively designed by all the competitors that were participating in the DARPA Spectrum Challenge. Sort of the collaborative environment where synchronization between independent networks was happening over these collaborative channels. We sort of said, hey, how about if we develop our STMs talking to each other and exchanging these parameters using the same concept. And that's what we started developing, and over the last couple of years, actually build a whole system based on extensions of something that the whole community worked on during the collaborative, the Spectrum Challenge. No, so anyway, I mean, this is just the illustrative implement, the idea of sort of looking at how this is actually working. And Gil, in interest of time, you can just go through this animation of the whole thing. And this was actually implemented in orbit. And this is really a fairly straightforward and simple implementation where we are trying to sort of come up with a channel assignment, non-overlapping channel assignment between three networks. Between three networks, and sort of creating a dynamic environment where, they could come in at different intervals in time and guarantee that they will not overlap and interfere with each other based on STM construct that they're exchanging. Now, of course, this is fairly straightforward and simple environment. There is plenty of bandwidth and channel availability. Things get actually much more interesting and much more complex once you start overlapping and introducing passive receivers, introducing stuff that does not communicate, and that's actually something that we intend to do in the NRDZ project.
So this brings us to the overview, just to put things in context. So now, we'll briefly start talking about, the planned activities both in the measurements and the SEMs and telemetry. So I'll quickly hand it off to Tingjun, who can talk about the measurement side.
Yeah, okay. So guys, we'll start from the higher layer applications that can be supported, using a combination of development in hardware and software. So here we're looking at a few applications in collaboration with the NOAA Center, as Fred was mentioning. The first one would be to protect passive receivers in the NOAA Center and operating at 1.7 gigahertz and also between 7.7 and 8.2 gigahertz. This is more for reception from a polar orbiting satellite. And actually, the NOAA Center in City College has observed interference when a satellite passes by, especially when it rises from the horizon near the George Washington Bridge, as you can see from the figure on the bottom side. And here we can actually use our software-defined radio capabilities, which actually includes expansion of the frequency range support, including the 6 to 7 gigahertz, and try to evaluate how the interference looks like from a time and space perspective. The second application would be to evaluate potential protection schemes of passive receivers that operate between 27 to 28 gigahertz. And this also is part of the FCC Innovation Zone that Cosmos testbed operating. And since we're building these mmWave transceivers, as you can see in the middle figure, we're also building a portable version of these transceivers, which can actually be used to study the interference that could potentially cause to these passive receivers and the radiometer. The interesting thing here is that this radiometer, which is shown on the left-hand side, has an opening from the top, and then there's actually a V-band receiver sitting horizontally within that wide enclosure. So any transmission within 27 to 29 gigahertz that comes from the ground level, or within a few degrees from the ground level, can potentially leak into the opening on the top of this radiometer. So that is one scenario that we plan to evaluate in terms of how much interference the ground level transmission using the 5G NR FR2 band will potentially cause into this passive radiometer receiver. And then, as Fred mentioned, there's also potential that we'll be getting some of these weather radar operating at 9.5 gigahertz. And Yvonne is also building a frequency expansion platform that allows the radios to operate to up to 12 gigahertz. So in that sense, we can also potentially study the interference at a frequency that is closer to 9.5 gigahertz. And as I mentioned before, another application here would be to study the coexistence between Wi-Fi 6E and 5G NR in the unlicensed band, especially in the 6 to 7 gigahertz, which is approved by the FCC for unlicensed applications. In this case, we're going to expand the frequency operating range of the software-defined radios that we have to actually cover 6 to 7 gigahertz. Yvonne has already actually done something along these lines. So using these expanded capabilities of the software-defined radios, we can actually also evaluate things in terms of spectrum sharing in the 6 to 7 gigahertz. So this figure here shows a diagram of how our software-defined radio looks like. So the thing colored in the red box is what we plan to add in order to support a frequency range that is about 6 gigahertz, potentially up to 12 gigahertz. So currently, the radios support up to 6 gigahertz, and with these additional capabilities, we're able to run experiments that covered, the new coexistence band between 6 and 7 gigahertz. The next slide, please. And here, this also shows a view of the various mmWave radios that we've built. So the most interesting part here are the portable 28 gigahertz radios that we have in the waterproof yellow enclosure, as well as the medium node that we just mounted on the City College building. And this actually is built based on the 28 gigahertz phase array antenna module developed by IBM in collaboration with Ericsson. And these radios have a fairly large RF bandwidth, supporting up to 1.5 to 2 gigahertz of real-time bandwidth. And using these radios connected to all kinds of baseband radio platforms, we can evaluate interference and transmission scenarios in these FCC Innovation Zone. And the next slide, please. And in the past 3 to 4 years, we have been doing a lot of measurements at a 28 gigahertz frequency range in collaboration with Nokia Bell Labs, essentially try to quantify the propagation loss and what is the potential coverage of 28 gigahertz mmWave in a dense urban area setting. And here we particularly look at different environments in Upper West Manhattan, which covers a lot of variabilities in terms of how radio signals would propagate in this very dense urban canyon environment. We have been collecting millions of measurements on different streets in different seasons, And based on the measurement results, we're able to quantify the coverage and the theoretically achievable data rates for 28 gigahertz millimeter wave scenarios. And some of the recent measurements that we've done also covers the area that's actually very close to the City College NOAA Center. And hopefully, eventually, we'll be able to use some of the measurement methodologies and the campaigns that we designed in order to evaluate the coexistence of 28 gigahertz commercial wireless with some of the radiometers that will operate at 28 gigahertz within that frequency range. Next slide, please.
Yeah, thank you. So I think this is bringing us to the set of tasks. Of course, this is mostly all proposed work that just kicked off the project, but I think Carlos can say a few words, and then Kyle can say a few words about it.
Yeah. So the goals that we proposed for task 1A are mentioned here. Once we got a hint of having a green light to start the project, we then started developing mechanisms to process some of the Cosmos 28 gigahertz measurement data that Tinjun just mentioned in order to generate SDMs for a couple of the streets where those measurements were collected. And as we're doing that, the idea is to have this process be super replicable and automated. So we started developing an API to really just capture measurements, and from those measurements start building the data processing chain to generate an SDM. Next slide. So for the 28 gigahertz scenario, so far we've built SDMs for based on the measurements collected on 120th Street and Amsterdam Avenue. Because it's a millimeter wave frequency, there's a lot of directional data in the measurements. That directional data can be placed in the SDMs, and it can be placed at different degrees of, let's say, accuracy. So we're going to be dealing with that, and then on top of that, we're building algorithms that use SDMs to do spectrum deconstruction. So in terms of the SDMs that we're going to be building, this is basically related to all the devices that have been mentioned so far. So the X-band and L-band receivers, the radio meter, the radars, and X-band are likely to come in the summer. Also for 6 gigahertz separation, as was mentioned by Tinjun. We're also considering building an inventory of the spectrum used within the radio dynamic zone. So for that, we'll need to characterize the emissions of Wi-Fi devices and maybe some cellular base stations that are in the radio dynamic zone, just so that we have that complete inventory and a complete view of the spectrum across the zone, and that the zone management system can use all of that information in order to compute interference events. So the other task is task 1C, which deals with the development of algorithms. So as I was kind of hinting before, since we start from one side, we're automating the generation of SDMs from just measurements. From another side, as was proposed, we're generating algorithms that use SDMs to perform spectrum deconfliction in a highly dense environment. So we have already started work and completed some work on a centralized based algorithm. I won't go through the details. The results will be presented in a recent paper that was accepted for WCMC.
Okay, yeah, so I'll pick up on where Tingjun and Carlos left off, mentioning 5G new radio, the 6 to 7 gigahertz bands, and also the coexistence with Wi-Fi. So what we have is a 5G telemetry tool that we are adapting to those bands for the purpose of this project. And our telemetry tool is called NG-Scope. It is as a monitor that can be integrated with the Cosmos hardware. NG-Scope is monitoring the control channel, the unencrypted control channel of the 5G new radio to extract very fine-grained telemetry information, finer than a power-based, most power-based spectrum monitors can see when they're looking at such a large bandwidth. Next slide. So we're getting insights that these devices, these power-based spectrum management devices can't extract. And do we have the next slide? And so the information that we extract is extremely fine-grained. It is millisecond level, and it is on the granularity in frequency of physical resource blocks, which are tens of kilohertz in bandwidth. So we anticipate that this information is going to inform the spectrum consumption models that Carlos told you about significantly because of its resolution. And as I said, it's the overall architecture of this is that the other parts of this project that are monitoring spectrum at much broader granularities will sense energy that is on a 5G band and then trigger the NG-scope part to tune in on one of those USRPs that Ivan mentioned, tune in and extract this extremely fine-grained information and feed it into the spectrum consumption model. So all of these components are really working hand in hand to build a very high-fidelity spectrum consumption model. Is there a next slide? I think I've reached the end. Okay.
The last component, Ivan will say 2 words about the ORAN and the algorithms, and then we'll summarize.
Yeah, and so last couple of years, we've been unofficially the ORAN and ONAP Test and Integration Center, and we actually have a permanent setup for both ORAN and ONAP development, and that's actually, they're quite heavily using the testbed, not just the dedicated part of testbed, but actually the entire testbed for various development tasks that the whole open source as well as closed source community is using. So anyway, that's Cosmos OTIC. And now as part of the NRDZ is actually our idea to sort of use this notion of ORAN that's based on software-defined radios that we have already, an ability to manage the actual frequency deployments of these highly programmable ORAN-based 5G deployments, to sort of try to integrate that with the dynamic zones and with our dynamic spectrum access, and sort of create maybe sort of fully deploy 5G in some of these NRDZ ranges and coordinate with both passive and active participants and sort of see if that can be actually done with the 5G components. And that's, of course, only doable due to the fact that it's mostly based on software-defined radios and the fact that we can move the entire 5G into sort of ranges of frequency where they normally shouldn't be operational.
Okay, thank you, Ivan. We also have a lot of activities on education and outreach, actually around spectrum, but given the time, I will not go into that. We can talk an hour about that. So just to summarize, the idea is that you heard almost from everyone, we'll develop and prototype a zone management system. The AMS is based on real-world measurements, SCM, telemetry, and spectrum sharing algorithms. We touched upon several of these and previous efforts in these areas. And we leverage Cosmos and FCC Innovation Zone for modeling, measurement, and evaluation. And as Ivan implied at the end, including ORAN-based implementation.